So it's my distinct pleasure to introduce you to Enrico Bini. He's at Santa Ana, Pisa, Italy. He's going to talk about optimal sampling for linear control systems. Enrico actually taught maybe over 1 or 2 lectures for us in this design flows course for control systems. So we needed some expertise in that area, so he helped us out, along with Marco from the same university. So I invited him, whenever he's in the United States, he's welcome to come and visit us. So I hope that we can actually start interacting with you more. My pleasure. So Enrico is an assistant professor at Santa Ana, and he's the youngest researcher with the qualification as full professor in computer engineering in Italy. In 2012-13, he was Marie Curie Fellow at Lund University. He actually worked with Carl Astrom and Carl Erik Arzen on cyber-physical systems and also resource management. In 2004, he completed his PhD on real-time systems at Santa Ana. He was awarded the best PhD thesis of the university. In January 2010, he also completed a master's degree in mathematics, the thesis on optimal sampling for linear control systems. He visited the University of North Carolina, Chapel Hill. If you remember Sanjay Barua, he came and gave a distinguished lecture at UConn. He also worked with Jim Anderson at NC Chapel Hill. And also India with Eves Sorel. He's published more than 80 papers, including 2 Best Paper Awards, 3 most cited papers at ECRTS. I don't know what ECRTS is.
No, it's one of the top companies.
Right. 1 most cited RTSS is the real-time systems, I guess. Real-time scheduling, operating systems, and optimization methods for real-time and control systems. His more recent research interests are in optimal management of distributed and parallel resources. So in fact, we talked about some of the problems that I'm working in the Navy that has got nothing to do with computers, but there's a lot of parallels in terms of dynamic scheduling and dynamic resource management. His service to the research community includes the organization of 9 events, participation in 51 technical program committees, and the review of 9 PhD theses and about 40 papers per year. Fantastic. They're all mentioned areas.
Thank you, Krishna, for the introduction. Thank you for the invitation.
Sure.
Right, so today I'm going to talk, first of all, please feel free to interrupt me anytime you want. It may take kind of 40 minutes, so it could be long, so just raise the hand. I'll try to answer if I know the answer, right? So let's keep it easy, right? Okay, so the talk today is quite deep into control. Since you don't know me, basically, let me just quickly have just one slide of personal information about me. Basically, it's what Krishna already said, so I may fly a bit quick on this. So I have basically 2 areas of research interest. One is real-time systems, which is the area where I basically grew up, where I got the PhD in 2004. And the scheduling, the keywords of my research area, my research in that area, basically I would say that like scheduling, real-time operating systems, resource management, CPU power management. That's basically, if I can try to summarize my research in that area with a couple of keywords. And I've been involved like most of my time in there. If I can quantify my current, effort in the area, I would say like 50%. Of course, this is kind of a random number, and it's kind of decreasing because I've been working in that area for already very long, and I'm kind of bored about that. And the second area in which I'm getting increasingly involved, in fact, I quantified like 40%, but increasing, right? And it's the control systems. I started to study in control when, the first paper I got in control is like 2008, but then in 2010 I also get a second degree in mathematics. Everybody is sometimes asking me, why after the PhD do you find the time, why did you carry so crazy to get a master in mathematics? Well, I have no answer to that, but I just, felt kind of, I wanted to diversify it a bit, so I thought, okay, let's do some mathematics. So for the thesis of mathematics, I studied control, and the thesis was on control, and that's basically the work I'm presenting today is, a summary of my thesis in mathematics. And in that area, the keywords, if you want, describe my areas like sampling, event-based control, scheduling-aware control. So, to schedule, what's the impact of schedule into control performance? Real-time control co-design. I also have a couple of papers, one of which I'm particularly proud of, which is TAC, transaction automatic control, which is considered the top journal on control, which made me very happy to have it, and also other papers, automatic and other papers. All right, now let's go into the topic of the talk. So first of all, motivation of the work. Why are
this is George?
Yeah. Hi, nice to meet you. So here, why are we interested in this? So first of all, in embedded systems, we know that CPU time, communication resources, bandwidth are severely constrained by the nature of being embedded system, right? And in embedded system, controller anywhere typically executed periodically. So periodically, you have timer, is interrupts, you read sensor, you compute the control action, and then you upgrade. Of course, periodic sampling is not necessarily optimal. That's clear, right? So you may have a system which is in a condition that does not require too much control action. So maybe there is no reason to check, periodically always. Is it everything fine? Yes, I'm fine, no problem. Don't check too often, right? So what's the lesson from this? And the point is that by removing the constraint of periodic constraint, right, we may save computational resource. We may save computation because we may avoid to sample and then to run the control law. We may avoid to do it during some intervals where the system is fine. There is no need to control. That's the point. So basically what we are going to do here is to investigate the problem of determining the optimal sample time control input that I denote by U bar in linear system. Very, very simple. Let me then define what is it for me, a sample time control input first. Sample time control input is something that any, I would say, high school student would understand, because it's just a step function. So it is a function. Here we are talking about a function that is defined over an interval from 0 to t, okay? And it has steps. So the points where the value of the function changes are denoted by t1, where t0 is 0. t1 is the first point where the value is changed. t2 is the second point where the value is changed, and so on and so forth. And so on until Tn, which is equal to the end of the. And also in UK, the input, the values, is the value of the constant. So U0 is the value between T0 and T1, U1 from T1 to T2, and so on and so forth. So this is a super simple definition, right? Just as a notation, sometimes in the next of the slide, I'm going to use also the notation for the intersample separation. So for this, the length of these intervals, right? And I'm going to use like tau k. Is that okay? No? That's fine. So tau k, I'm going to is defined as tk plus 1 minus tk. So t is the absolute instance, and tau is just the separation. So the notation, I hope, is clear to everybody. Right, and you are the values. What is the problem here? The problem is this. So given an interval of the length of the interval, t, and n big N, which is the number of samples that the number of intervals that we can use in that interval, so the number of sub-intervals, and given a linear system defined, as all the linear systems are defined, so x dot equal to ax plus b u bar. So in this case, the input u bar belongs to the same class that we've seen before. So u bar is a sample time control input, okay, and given an initial state. So what is the problem? So with the x being the state as usual, we want to find what is the optimal sample time input u bar, so this guy here, which minimizes a standard quadratic cost. This is very standard quadratic cost in control. It's called, it's in the linear quadratic regulator problem. So basically, what's the intuition of this cost? I hope you can see. So we want, since we are integrating this cost from 0 to t, we want the state to be 0, right? We want the state to go to 0 as fast as possible. But we want it to go to 0 without making a too big control action, because without this term, basically we can use u bar arbitrarily large and make the state go to 0 very quickly, right? So we need this term to also to give a weight to the type of action that we are doing. So this is the intuition of this cost, okay? This is quite, who of you have seen like this cost before? This form of the cost? Good. Oh, that's good. Okay, no, that's fine. Just to check the audience. Excellent. That's a standard quadratic cost. So the problem, finding the optimal u bar is then equivalent to what? It's equivalent to find the optimal n input values and the optimal n minus 1 points where we have to change the value. Because, this is it's a unique representation. Okay. Okay, first point. First point is that if the instants are given, finding the optimal UK is easy part. So that's the first point I want to make. Why is this true? So if the tau k are known, so if we know already, well, tau k and of course tk, so if the instants are known and only the values are unknown, okay, then finding the values is, the optimal values is a problem that is studied since long time. Because what we typically do, we discretize the system by every step, and we discretize in a way that is dependent on the length of the interval. So in the first interval, we discretize by tau 0, then we discretize by tau 1. So at every interval, we discretize with the appropriate length. And then here, of course, we transform it into a time variant into a time variant discrete time system, okay, where you have xk plus 1, which is basically the sample of the state and the separation. So we have here a discretized dynamics, okay, but it has an index k, which is represented by the fact, which represents the fact that it depends on the length of tau k, okay, and this problem can be solved easily. So it's solved the standard technique, so no problem here. Right. So finding the input values is not the problem. So the problem just reduced to finding the instance, because once we have the instance, the optimal inputs is standard.
Of course, the QK bar and RK, they depend on tau k. Right?
What?
So those discretized matrices involve some integrations too, right?
Yes, it depends on integration. Yes, all this.
And you get the cross term also, which you didn't have before.
Yes, you get the cross term, you do get it. Right. So the problem is finding a sampling instance that minimizes the control cost J. Okay, let's review then some existing techniques. The first existing technique, quite, I would say almost unique sampling technique, is periodic. In periodic, what we do is that, we decide the grid here of, we uniform sampling. So we have t, we divide it in n subintervals, and then those are the sampling instants. And then, thanks to the techniques that allow us to find the value for a given grid, we find the value. And of course, no surprise is if we realize that, the sample time control input mimics, if you want, the continuous time optimal signal. This is quite expected, right? Because, if the continuous time signal goes, let's say, that way, then no surprise if the optimal sample time control input mimics that signal. Right. A second method to control that I would like to to think about is what is sometimes called Lebesgue sampling. In Lebesgue sampling, basically, we can view it as a sampling along the y-axis instead of the x-axis. So we distribute sample uniformly along the y-axis. This leads to what? So at the points where this uniform grid hit the signal, we derive the sampling instance. And then once we have those sampling instances, by invoking the optimal procedure that computes the value here, we can find the value up here. And that's the type of signal that we would get. All right. Let's go to optimal sampling, but let me drink a bit of water first. All right, so if our aim is to find the optimal cost then and the variables are the intersample separation, so the length of those intervals. First, what we have to do is to find a way to write the cost as a function of the variables. That's the basic of any optimization. So, I mean, here I'm not providing the details of what is this expression, because it's extremely complicated, and there is no value in projecting here, like, layers of equations. But then the strategy, in this case, is very simple, right? So one can compute the cost here as a function of the intersample, and then, of course, we can compute the gradient. The gradient, so how much does the cost vary when we perturbate a bit the intersample separation. And then what we want also to enforce the constraint, so we want to enforce is the sum of all separation is equal to the length of the interval, otherwise we violate the problem formulation. So very easy, we apply Kuhn-Tucker conditions, and then we can find a local optimum, because here we don't know it's local or global. A local optimum certainly must satisfy a condition of gradient equal to 0 and staying along this constraint, which we can write in this way. Right, so what's the point here? So if here these conditions are necessary to be optimal, right? We know KKT conditions are necessary. So what one could do is that I give you a solution. So let's say the first natural question we had is, let's plug the periodic sampling and the Lebesgue sampling into this condition, and let's see if these conditions are satisfied. If these conditions are satisfied, then there may be the chance that at least they are local optima, right? What we did is that we actually, if we plug those samplings, so the periodic and the Lebesgue sampling, into the necessary optimality condition, we verify that these methods are certainly not optimal. Okay, so that justifies like a further research, because I mean, if those are not optimal, maybe we can do something better.
So in essence, you need to do the condition 2 is sort of telling you that you should do Lebesgue and J rather than the y or the x-axis, right? That's basically what that condition says. So.
I should say.
So think of in terms of discretized gradient. So it's basically J at T.
That's the derivative.
Yeah. So the derivative basically says that the delta J.
The variation of J with respect to one interval here must be the same to the variation of the cost with respect to the next interval.
Right. So basically the slope of your J with respect to the thing should be the same. The delta J divided by delta tau, right? The delta J divided by tau should be constant.
Delta J divided by delta tau should be, well, the component, I mean, that's the H component here, the H component of, this is a gradient, right? This is a vector.
Right.
So the H component of this vector should be the same as the H plus 1 component of this vector.
Right.
That is what we said. Right. So what one could do would certainly do. Okay, we have a gradient. Okay, let's do gradient descent. Let's see if we can improve. And so that's what I did. We did some numerical optimization, and so there was some issue here, right? So first of all, the numerical solver was extremely complicated. It took a lot of time, and also the problem is not convex. So I mean, we may improve one of those methods we started from. So you can start from an initial good guess. You can do a couple of steps. Maybe you can improve. But of course, no convexity does not guarantee any optimality, right? So we thought we wanted to do some alternative strategy. And here is the alternative strategy. Right, so this was an idea that came to the other author of this paper is a mathematician, is Giuseppe Buttazzo, and that's this idea that he had. Completely new problem. Let's forget about, for a couple of slides, let's forget about the previous problem. So what's the idea? So first of all, we know that as the number of samples increases, certainly the function, the optimal sample time input u bar, so the function, the step function, certainly is going to tend to the well-known optimal continuous time u opt. So as I plotted like in the couple of slides before, there was like a signal that was like the continuous time optimal input, and if the number of samples increases, then the sample time input will have like it's always smaller and smaller steps, and in all those smaller and smaller steps will mimic closer and closer the optimal continuous time input, right? Okay, good. So that's the idea. So the idea is that motivated this second approach is what about trying to approximate the optimal continuous time u opt? So we take the optimal continuous time u opt and we try to approximate it as close as possible and check what type of control do we get. So to do this job, I need to define this quantization problem. Quantization problem is standard in many areas, and basically quantization is all about approximating functions. So in a quantization problem, the typical problem is that we have a function, like here, like u opt, that is given, okay, and we want to find u bar t, so we want to find a piecewise constant function such that the error between the target function and the approximating function is minimized, where the error is a standard quadratic error. So here we just integrate the quadratic error, no strange things. I mean, this problem is very standard. So this problem has nothing to do with control. The only link to control is the starting function, okay? But then once the starting function is given, we just approximate it, and we don't know anything about control. Okay, so I have to introduce you to the result that we have found. I need to define this concept, the concept of sampling density. Sampling density intuitively is really what the name says. It's a density of sampling instance, right? So how do we define it? So for a given sampling sequence, let's say 0 to 1 to 2 up to the n, we define the sampling density, sigma n, as this function from 0t to the reals, defined this way, very simple. So 1 over n is just for normalization, 1 over n and what? And the length of the interval. So this means that the sampling density for all points within an interval that is very narrow is going to be very high. The sampling density for all points within an interval that is a bit wider is going to be very low. So this is really represent the sampling density. So if you are given like points here, we define sampling density in this way. This is definition.
Basically, area is the same.
This is?
Area is the same.
Area is the same, 1 over n. Exactly. And in fact, I want, we have this n normalization factor so that the integral is 1, right? So we can make the limit and, not alter the area. Good. Of course, also we define the asymptotic density, the asymptotic sampling density of a sequence of samples as this, as the limit, as n goes to infinity, of sigma n of t. So this is going to be a function, it's going to be smoother, right? So I hope you believe it, that if we have periodic sampling, what sampling density are we going to have? In periodic sampling, all samples are equally distributed, so all intervals are the same. If all intervals are the same, the level here is all the same, and no surprise, it's going to be a constant, so proportional to 1, that's dependent on the interval, right? For in Lebesgue sampling, what type of sampling density are we going to have? That's something a bit more intriguing. So if you are going to approximate a function, you remember Lebesgue sampling. Lebesgue sampling, we were throwing uniform arrows on the y-axis, checking where those arrows were intersecting the function to be approximated, and verify, and define the sampling instance along the x-axis, right? So the asymptotic sampling density for the Lebesgue sampling then is proportional to u, the signal, to the derivative, to the modulus of the derivative of the signal, because that's quite intuitive, right? So if you have a signal that grows very much, when you plug here, on the y-axis you have uniform sampling, then when you go on the x-axis, the samples are denser. If you have a function that is closer to be flat, when you have a uniform sampling, uniform points along the y-axis, when you see like their image on the x-axis, the points are more spread along the x-axis, right?
This is basically the Shannon. It's going to the Shannon sampling. In a sense, because u dot is basically the frequency. Right?
Yes, exactly. All right. So why did I need to introduce this? There is this very nice result which I was not aware of, and this comes from my co-author was aware about this result. That is as follows. So when n goes to infinity, the sampling density of the solution of the quantization problem so let me just say it slowly, right? The solution of the quantization problem is the solution to the problem where we want to minimize the quadratic error. So we are given a function. I'm sorry for Adam, it is, but...
Yeah, it's right there.
I can erase it.
You can erase Adam.
Sorry, but... Yeah.
Probably some liberal arts people.
No, I'm happy.
I don't think the engineers will do that.
No, I encourage liberal arts, but Right. So let's see. So what's the message here? So here we have a function, and the goal was to find something that let's say minimize these areas here, right? I mean the integral of the square, not exactly the area. The area is without the square, but we understand, right? Okay, let's stop it here. And so basically what that result is saying is that if I send n to infinity, these points here, so of the solution, of the optimal solution, are going to be distributed along the interval proportionally to u dot, so this is u to the derivative of this, modulus to the 2/3, okay? That's something, the 2/3, it was something unexpected to me. The mathematicians are good at this, so I read their paper. Sometimes I don't manage to understand it either, but I was lucky enough to have worked with the mathematician, so he told me, okay, this expression means 2/3. Okay, good. So basically we took this result to do what? To build what we call here quantization-based sampling. What's the idea? The idea is this. Number one, we compute the optimal continuous time input from the control. This we know how to do it. We compute the u dot modulus to the 2/3, which is exactly this function. So here we have this function, we make the derivative, and this is the modulus, and then 2/3, okay? And then, based on this, we divide all this density in equal areas. So we have an area here, from 0 to t, we have some area. Since the samples are n, we want to divide that area in n equal sub-areas, sub-regions. And so we define these points as those points that separates regions of the same area, or the same area equal to 1 over n. Okay? And then what then? That for these given points, we know from given points how to compute the optimal continuous, the optimal values UK. It is from standard theory. And so this is what we do. Okay? This is the strategy. All right. Then, the first point is, okay, look. This strategy sounds like this. Okay, I have a problem. It's difficult to solve. I don't care. I solve another one. So that's it looks like this. So the natural question that here I would have, if I would be viewing like this presentation, is okay. Look, but what is the relationship between the original problem you started from and the new solution of your new problem? Okay, so what we realized is that, quite surprisingly, the cost of this quantization-based method was much lower than any other method that we could think about. And also the norm of the gradient at the quantization-based, the solution produced by the quantization-based sampling was suspiciously small, okay? Kind of indicating that it may be a local minimum. All right, so the link between these two methods was not only numerical, but fortunately to us, we also managed to prove something, okay? We have a proof. So what did we prove? We proved that for first order system, so super simple, right? So the matrix A is just a number, okay? When you have to prove something, you have to make some assumption, right? For first order system, the asymptotic density of the optimal sampling, so I'm talking here about the optimal sampling minimizing the original cost J, not minimizing the quantization. So the asymptotic density of the sampling minimizing the original cost J is the same. U optimal, the derivative of U opt modulus to the 2/3. So basically, here's the situation. We had this complicated problem. We don't know what to do with. Inspired by this, we started to solve another problem. We know this problem has this solution with 2/3. We realized, we proved actually, that the solution of these 2/3 is a solution of this original problem in some special cases with this hypothesis, okay? That's basically what we do. So, just a proof sketch. I have like 4 bullets. This proof is like 3 pages long in double column format, so I'm not feeling good to prove it here, but I'm just giving the sketch. So, what was the proof is like? So, if n is equal to 1, then the condition of the gradient was a bit simplified, pretty much, because you have to imagine that the gradient as a function of all the sampling interval, there's a lot of exponential matrices, it's a very big monster. But if n is equal to 1, the exponential of matrices becomes exponential function. So e to the function, right? So when n goes to infinity, because that's also another hypothesis, we proved the asymptotic, the property of the asymptotic density. So we could exploit the property of n goes to infinity. And when all n goes to infinity, all the exponentials can be approximated quite accurately by polynomials, right? So using the Taylor expansion, as usual, if you want. So basically, the condition, the 2/3 was found. I mean, the fun part of this proof is that we did not plug 2/3 in there and demonstrated it to be optimal, right? The 2/3 came out by itself, okay? Which was, I mean, quite good to us, right? Because, I mean, if you put 2/3 there, you know, you may, you know, I like much more this way, right? Because, you know, you don't make any previous hypothesis. It could have been like 4/5, I don't know. So the 2/3 came out by itself. And yes, and this result holds regardless of the other, you know, A, B, Q, R, or the other parameters of the system. It also, you need n equal to 1.
So the thing is, can I do this adaptively as time goes on? So
yeah,
you need to have the t fixed before.
Exactly. So that's the point. So this was of course, the weakness of this approach is this open loop nature, right? So we have t, you have n, and you do this. So adaptively, to do it online, we have a paper after this in which basically we construct an event condition based on this rule. So we sample the system, we have a state. From the state that we have sampled, we project what would be the optimal continuous time input from that state. We build it. Then, based on that, we define when the next sample is going to be. And at the next sample, we reiterate the procedure.
So that's MPC data.
Exactly, kind of MPC. But you know, we don't go too much further ahead of time. Good. Of course, you know, once you start to eat something good, you want to eat more, right? So now, here we have the proof for n equal to 1. Natural question is, what happens for higher order system? N equal to 2, 3, 4, 5. Oh, well, no proof for a bigger n. No proof for bigger n, but some experimental results. Let's go into the experimental results and let's view them. So here I'm going to talk about the experimental result, but before that, let me drink a bit. All right, I'm going to compare periodic sampling, Lebesgue sampling, this Q23, which is based on quantization, and the optimal sampling based on gradient distance. So that is a real numerical monster, right? And what do we use to compare those methods? Actually, that's a bit complicated, but you know, we'll find a way. So as n goes to infinity, basically the cost of any method tends to the continuous time cost, because as you increase the number of samples, all signals, you know, will be smoother and smoother, and will tend to the continuous time cost. So how do we compare the cost? Basically, we compare the cost by speed of convergence of the cost of the given method to the continuous time cost. Okay? And so basically, there was this result that is like in the 71 by Mercer-Kuo, which proved that basically the cost in periodic sampling, the cost, yeah, here maybe it's. Yeah, I can write it here a bit better. So the cost of a method m is equal to the cost of the continuous time plus some coefficient, I call it like Cm, yeah, with you know, tau square. So with the square of the period, right? So when the period go close to 0, then so basically the cost tend to the continuous time with the second order. So there is no first order here. So then the question, the only number that is reasonable to play with is to compute the Cm value. I mean the coefficient that goes here like in a Taylor expansion. And we define it as this asymptotic normalized cost, right? The funny thing is that this asymptotic normalized cost has also a very nice engineering interpretation. And I think that's quite interesting. That's the reason. So we have if we write the cost of some method in this way, so with the continuous time cost times 1 plus, this extra term that depends on the fact that we are sampling and depends on the method. Okay, this is what we do. So you can basically, we can answer to some question like this. Suppose the designer said, okay, I want to define a method which tolerates a cost increase of R% with respect to the continuous time cost. Okay, so I say, I know that in theory the continuous time cost is this, and I can tolerate up to 5%. So basically what this guy wants, it wants that the cost of the method minus the continuous time cost, so this is the cost increase, clearly, relative, okay, so we divide it also, we make it relative number, which, thanks to that definition, is exactly Cm t square over n square. You bring this here, so you do the math, that's exactly what it is, right? You want this to be less than R, than the tolerance, okay? And so this leads to also the number of samples. So this answers to a very interesting question. How many samples do I need to use to respect this constraint of tolerance? So, and it is very interesting because, of course, the number of samples is growing linearly with the interval of time. No surprise. The longer is the interval, the more sample I expect. I expect it to grow it linearly. It grows with a square root with Cm, and Cm basically represents the quality of the method. So the quality of the method is entirely coded by this number. The higher quality, the lower is this number, because the closer is, the faster the method is tending to the continuous time, and the fewer samples we are going to need. Also, the smaller tolerance we want, the higher number of samples. No surprise. So this is also, I think, it provides a quite interesting indication from the engineering point of view, I would say. Okay, now it's time to investigate this number, this Cm. This Cm is really the number of interest, right, for each method.
But this was for a constant t, though, right? The Mulzer score. Because I remember looking at all this stuff, because we published paper 78, I think, in Automatica, one of our first papers, where how should you implement a continuous controller in digital domain? We found that to use the average control, that tends to work better than what the Ko and some of his team had done with that. So we can talk about offline.
Okay. Okay. So, but this is...
this T is constant here.
T is constant, yes, T is constant. It is a parameter given, yeah. Still open loop, known in advance. Okay, so let's compare the methods. Here we have a second order. So basically, you have a method A, B. So first, I just compare like the solution. So how the points look like over time. And here I also have like the number, the cost, the asymptotic normalized cost. So periodic, no surprise, we have something like this. Lebesgue, we have something like this. So basically, the points a bit denser here. The cost the decrease with respect to periodic. If you do this quantization, actually the cost decrease even more, okay? And you can notice the effect of the 2/3 operator, because 2/3, so the density of this guy here is the derivative to the power of 1. The density of this guy is the derivative to the power of 2/3. 2/3 is less than 1, so it's natural to expect that when the points here are denser, here are a little bit more spread out, while of course the periodic are uniform. So in a way, since the exponent here is 2/3, the exponent here is 1, the exponent here is 0, because of course,
Constant, yeah.
then this has to be kind of in between these two intervals, these two densities. And if starting from this solution, we run the gradient descent, the gradient descent cannot improve basically too much, and the improve of the cost is this, and the quality of the solution is, visually the same. Right. So to perform a more deeper comparison, basically we have developed a generalized sampling rule in which the sampling density is just u dot modulus to any alpha with alpha between 0 and 1. In this way we can compare all the methods. We know because with alpha equal to 0 we get periodic sampling, because alpha equal to 0 means a constant, means uniform sampling. With alpha equal to 1 means Lebesgue sampling. It means to sample according to the derivative. So when it grows, you sample again according to the derivative. With alpha equal to 2/3, we have this optimal sampling. Yes, if you believe in 2/3. And so what happened in the next plot is that for each alpha between 0 and 1, we are going to evaluate the asymptotic normalized cost for the given method. Okay? Okay, so here we have again a system. We have n equal to 1, a, b, whatever, all numbers. Actually what we find is exactly this plot that I found very interesting. So basically, since we proved that this was the minimum, if this was not the case, maybe either the proof was wrong or the experiment was wrong. So I was very happy that this experiment was effective, right? All right. So this is confirms the validity of the theorem. So that was good. Okay, and then the question is, 2/3 appear to minimize the cost. What happens with n equal to 2? With n equal to 2, we have no proof. So the minimum could be everywhere, right? So here we have some system. Actually, we are introduce some oscillatory behavior because we have some omega. So basically here we are playing both with the frequency of oscillation as well as with the weight to the state. Okay, Q. Okay, so if we do this, basically we find this plot. We find this plot here. The different plots are for different values of omega and Q and some parameters. And this result made me quite happy too, because this numerical simulation demonstrated, of course, in this case, demonstrated not like for all possible cases, that 2/3 seems to be the minimum even for n equal to 2. Maybe n equal to 2 seems to you very restricting, but to run this experiment, since we have n equal to 500, you have to imagine that in an interval of length, maybe 1, I don't remember how long was the interval, we were running this so we had all those points, and we were iterating gradient descent, for all these points. So this took maybe 2 days of my laptop time. So n equal to 2 only was really time consuming. If you have time on powerful machine, I have the code to run it for as many as you want. Okay, it's time to conclude. So what happened in this presentation? Basically, first we derived the necessary condition for minimizing the cost, which was based on the gradient, the most natural and the first thing that one would do. And then, yes, we proposed a method that wants to approximate the optimal continuous time signal. And we demonstrated that this method has the same solution, is optimal for n equal to 1. In the future, the future here is really open because we may want to investigate the problem optimal observation instance when we want to estimate the state. That's also it's called the dual problem in control, when you have the sampling problem and the dual is the observation problem. And another option could be also to find a more efficient numerical algorithm to find the optimum, because I'm not an expert in numerical methods, but maybe there are people who want to do that. And this is everything. This was this paper on transactional automatic control.
Yeah, we got a lot of things to talk about. We worked on this kind of problems from the human viewpoint. In fact, maybe you may want to connect up to a lot of the work in human sampling thing.
Yep.
So way back, a guy called Sanders started in 1954, and there were a whole series of work that was done in this area, like how often a human should sample. And so it started out using related to Shannon sampling, queuing type models. And so this has got a lot of applications, I think, beyond what you've done.
Yeah, I'm sure.
And also, this is also related to like how many points, if you want to tabulate a function. I think there's another application where one of my students had worked on that.
How many
points you need to represent a curve.
Yes.
So Bellman did that work way back in 57, and also the guy called Brian Bluss in the 1960s. So I really like your 2/3 thing, I think. So there could be some lot of cross fertilization.
The two thirds was something that when I when I saw it like from the mathematicians, come on, you should have been telling this like to everybody, right? You know, everybody wants to know how to approximate any function. That was exactly the thing. And I think that was the last slide. Okay,
it's fantastic.
Yeah, thank you for your attention.
Yep.
And then, if there are other questions, I'll be happy to take them.
So just a quick question. In your comparison, you showed the different CMs, right? The CMs are different measures, right? What about in terms of your cost?
Here.
So here, right.
Yeah, the cost depends on...
cost is a function of CM, right?
Yes, exactly. The cost is a function of CM in this way, right?
Oh,
so
the infinity is the same.
The infinity is the same because the plant is the same. And then you plug CM here. Basically, CM.
Okay, from there you can get.
Exactly. So the CM measure just like the speed of convergence, because as n goes to infinity, I mean, they will tend to be the same.
It's just another way of representing.
Exactly. It's the extra, the difference between the continuous time and the cost of the map.
I think there is also an application for video streaming stuff as well. Okay. So there's some quite a bit of collaborative thing that we can do.
So basically, you could decide, not periodically decide
your R is
change,
going to be
right? Rather you sort of change.
Right.
Yeah, and maybe in that case it's hard to. I mean, what is the function? Let's say that the function. In video, right?
Now we had done some work in state estimation, so maybe relooking at that problem.
Yeah, something I'm thinking that the 2/3 comes from two numbers actually. That's maybe something I could add here. The 2/3 come from these two. That comes from the dimension of the image space of the function. In this case, the image space of the function is dimension 1 because it's just one line, right? So basically, and so if you want to minimize, the integral from 0 to let's say something, so the difference to some p, okay, so some p norm, and the function.
Is always p by p plus 1?
No, p divided p plus d.
D, okay.
Where d is the dimension of the image space. So if in MPEG decoding, you can view it as a 2D function.
Okay.
Then d may be 2.
I see.
Here d is 1 and p is 2, so we have 2/3.
Right. So that means you can have multiple objectives, is what you said.
Exactly. So, but my understanding of better by the mathematician, which is still something that I have to go deeper. My memory is that it comes from something like p over p plus d, where d is the dimension of the image space. So if the image space has like 2 dimensions, then the image measure, something has to do with the measure, I don't really remember. But maybe with images, if it's 2, then you may have like 2 here.
Yes.
Don't know.
Okay. Are there any questions?
Are there any results for nonlinear systems? Are there any results for nonlinear systems?
Oh my goodness.
It's very hard.
I proved it for linear and n equal to 1. So what do you want? It took 3 pages. So,
well, of course, giving a proof is much harder.
Yes, exactly. I mean, if you want to run simulation, you know, if you have computing time, let it go. But it's hard then to, you know, to understand it. I don't know.
Okay, so he has got some time constraints, so are there any other questions? So you may want Niranjan to take a look at it. I'll get the papers from him, because his problem is exactly this stuff, you know. So there may be some common things that we can do together.
Yeah, I'll be happy to. So the paper is this one, but you know, I think the presentation is.
Yeah, you said January 2014, but
Yeah.
but maybe there is. We can talk about some of the problems.
And the paper that you well, at the beginning you said is open loop, and of course it is. I was saying that we have like this paper in which we make it like an event based condition.
Yeah,
and I can point to you to that paper.
All right, thanks a lot.